Hey folks, so welcome back to another lesson, and today we're going to look at line spectra. So I'm going to expect you to be able to describe what a continuous spectra looks like, identify absorption and emission spectra, state that each element has its own unique line spectra, and use line spectra to work out the elements that stars are made up of. So quite a lot of stuff to cover here and some quite interesting things as well. So first of all, get you thinking a little bit about this. What happens when we heat up a piece of metal? Okay, so hopefully you're able to tell me, or even just looking at the picture here, that when you heat a piece of metal, it gives out light. And in fact, you might even be able to tell me that the hotter the element, the heat of the metal, the different the color that the metal will give out. And you can see that the hotter it is, the closer to white that the light that's given out. And you might have heard of that expression, he's red hot or that's white hot. So all hot objects like stars will emit, which means give out radiation, and hot objects will emit a continuous range of frequencies of light, i.e. there's no gaps in the colours, called a spectra. So in other words, this is what a spectra looks like. It looks like a band of colours where you can see there's no gaps in between it, and that the colours almost seem to meld from one to another. Now, this idea of frequencies, I'm going to come back to later on when we do waves, so it'll make more sense as to why I'm saying frequencies there. Now, what does this photo remind you of that is also a spectra? And you might have seen this in the sky. Now, hopefully you're able to tell me that the other thing that looks like a spectra is, of course, a rainbow. And a rainbow is an example of a real world spectra. Okay, so how do we get the spectra? Well, you've probably done this experiment in for second year, but if you take white light and you pass it through a prism, a glass prism, then depending on the angle, you can usually get a spectrum of light coming from that white light. And rainbows are formed in a similar way, except you're not using a prism, you're using water droplets. Now, to show you that's actually true, if you've ever looked at a garden hose and you've got a very fine spray coming from the garden hose and there's light, sunlight passing through it, you can sometimes see a rainbow. And that's the same reason why if you go to some waterfalls, depending on the light conditions, you can see a rainbow close to the waterfall because it's actually white light that's being split into a spectrum of colours. Now, this spectrum of colour is really, really important because it's part of our electromagnetic spectrum, which you might remember seeing from the last lesson. Now, it's special because it's the only part of the electromagnetic spectrum that we can see with our eyes. And so, because it's visible by our eyes, we call it the visible part of the spectrum. And this is the only bit that we can detect with our eyes. We can kind of detect infrared because it's heat energy, but we can't detect any of the rest, at least not directly. And again, when we come to the waves topic, we'll do this in a bit more detail. So, how do astronomers or physicists get spectra? Well, they use this really crazy looking device called a spectroscope. And the idea, you can probably see the prism there, is that you let a beam of light come in, then the prism will then split that light up into the spectrum of colours if it's there, and then you can look into it to see that spectrum. Now, I do have much more simpler spectroscopes in class, so I'll try and show those to you when we get back into class. Okay, so what are the different types of spectra? Because there are actually three types. Well, the first one, the continuous one, we've talked about that already. You get two other types called an emission and an absorption spectra, and the names really come from how they are produced. What's interesting is if you look at the two, you can probably see that if I was to add these two together, you would get a continuous spectra again, wouldn't you? So an emission spectra is complemented by the absorption spectrum. And complemented just means if we combine them, we get a continuous spectra. So how do we get these types of spectra? Well, a continuous spectra is just when the light from the sun or an object is directly seen by a spectroscope. So if you like, nothing really happens, you just see the pure light as it came out from the source. An emission spectra is made when light from the sun passes through an element. So an element, in this case, we're talking about a chemical element like hydrogen, and the element then gives us light back out, or at least some of it, in a specific color. And each element will produce its own unique spectra. So for example, here we have the spectra for helium, neon, and argon, and can you see how there are very specific colors and specific bands for each element. Now, because these are lines, we usually call this line spectra. Absorption spectra is kind of like the opposite of emission spectra. They're made when the light from the sun passes through an element again, e.g. hydrogen, and then the element absorbs the light of specific color, and the remaining light is then observed by the spectroscope. So again, each element will produce its own unique spectra. And so for hydrogen, so this is the spectra for hydrogen, you can see how it's missing some colors because those have been absorbed by the element. Now, what is the application? What is the use of this for astronomers? Well, because these spectra are all unique to each element, then you can think of them as being a bit like fingerprints. And so what astronomers can do is they can look at the line spectra of light coming from different objects in space, and by looking at the specific pattern of the spectra, they can then identify what elements were present. So it's a bit like going to a crime scene and looking for fingerprints to see who was there. So how do astronomers use this? Well, astronomers compare the spectra from the sun with spectra of elements on Earth, and this lets them work out the elements which make up the stars. So it's a bit like fingerprinting, as I said. So to show you how that's done, if we look at the stellar spectra, so this could be a spectra from the sun. We've got the spectra of three elements on Earth, so hydrogen, helium, and sodium. And the idea is that we look at the elements on Earth and see if they appear in our stellar spectrum. So sodium is the easiest one because we've just got this double band here. And you can see if we look directly above it, it appears there. So that means this stellar spectrum has sodium inside it, or this sun has sodium inside it. If we look at the hydrogen one, we can see there's three unique bands here. And again, they're found inside that spectrum. And so this sun probably contains hydrogen. Then the final one is helium. Again, you can see that matches up, and that matches up, that matches up, and that matches up. So again, this sun also contains helium. Now, most stars actually contain hydrogen and helium, and we might look a bit about that later on when we do radiation. And then here's an example. Below is the emission spectra of four elements and the spectrum of an unknown sample of gas. Which elements are found in the unknown example? So have a go with this yourself. I'll go for the answer with you once you've tried it. Okay, hopefully you get the idea. It's basically just comparing to see where the lines are the same for each, for both spectra. So here, let's look at helium. We can see that matches that one, that one, that one, that one, that one. So it definitely contains helium. Sodium, well, we're missing this band here, so sodium can't be present in here. Hydrogen, we can see, yep, again, bands match, so there's definitely some hydrogen inside here. Lithium, well, this one's a bit weird because it's almost there, but it's not quite. Here, it's definitely not present. Here again, it's not quite lined up. And this one is a little bit out, but on the whole, because we're missing this one and this one, we could say that lithium doesn't appear in it. So the two elements that appear in this gas is hydrogen and helium, and that's how we use the line spectra.